Now, I talked about I/O as being one kind of computation. It does side effects, but we can think of other type forming operations, other functors, as computations themselves. We can think of maybe A's as computations that might give us a result or an error, and we've been using it like that in what we've done earlier in the course. We can think of lists of A as computations with multiple results in A. So they could be a non-deterministic program where we collect all the possible results into a list. And we could also think of there's a thing called the state monad, which they're computations which return an A, but they also, in the background, there's a state of type B that is modified. So in the first case, the side effect is you might not get a result. The second case, it's a side effect of having multiple results. The third is you've got a state being manipulated. But these are all different kinds of computation, if you like, and they all have the property that you can turn an ordinary thing into a thing of that type, and that you can sequence those kind of computations together in a sensible way. And that's what we do by defining the greater than equal operator, which is sometimes called bind. And I'll explain why in a couple of slides' time. So what about the instance for the of monad for the maybe type? Well, return of x, we just apply just. So it's the return of x, the thing that converts us from the type into type A to type maybe of A, we just apply just. Now, what about applying bind or greater than equal? Suppose the first thing returns an x, just x. Well, then we'll apply f to that x to give f of x. And in the second case where f has, where the m of a returns nothing, then we simply return nothing. So what that does is it applies f if there is a value to apply it to, otherwise it returns nothing. In the case of lists, what do we do? How do we inject an element into a list type? Well, we just have the singleton list. Now, what about the case where we return a list of results and we have this function f to apply? What do we do? Or we apply f to everything in that list, and each of those answers will be a list, so we concatenate the result, that list of lists, into a single list. So we do a map followed by concat, or if you like, we can define it as a list comprehension like that. We choose an element from the list x's and we choose an element z from the list we get by applying f to x. Those equally well define, those two definitions are equivalent. And it's a way of, if you think of a list monad as a multiple computation, we have multiple arguments. When we apply f, we get multiple results there. So we have to deal with those two levels of multiplicity. So we map to get a list of lists and then concatenate that list of lists to get a list containing all the possible answers of the overall computation. Now, obviously, the type I/O has a return and it has a bind, but those are built in, so I'm not giving you those definitions here. Now, why do we call this operator bind? We'll see here. What happens, and it also it allows us to explain what goes on in the do notation. So let's have a look at this simple example in the middle on the right hand side of the slide. We've got a do where we have some monadic stuff returning R, we get the R value from that, and then we do a computation involving R. What is that shorthand for? Well, it's shorthand for monadic stuff returning R, bind, and then the function taking R into that computation involving R. So the do notation is another way of writing the binding of R to the result of the first part of the computation. What we do in the unsugared, in the notation where we don't have do, is we have a an expression returning R, and we bind that to a function, lambda R, which then does the computation that involves R. So behind the do notation, where I wave my hands rather about how it worked, is this definition where we replace this binding to R by passing to a function. And if the first computation doesn't return anything, we simply sequence with the constant function of doing whatever comes next. So that is, underneath the do notation is this bind, greater than equals operation. And as I explained earlier, I find the best way of understanding that is to think of it as a way of sequencing together functions that do side effects. Now, there's quite a lot of stuff in there. I haven't talked about the state monad, for example, which you can find information about that in the book. But I guess the crucial thing here to understand is the notion of a monad as a form of computation. I think the examples of lists and of maybe are quite evocative examples. You know, computation that may not give you an answer, computation that could give you multiple answers, and then you can see how bind is defined in those cases to do exactly what you would expect. And in the case of the state monad, what you do is you do some computation in the first function and then use that, the result of the updated state, when you invoke the second function. So you thread the state through those two computations. That's how bind works in that case. Okay, that is a high-level summary of monad, but I think the insights of a generalization of function computation, function composition, and a thinking of these as general computations with side effects should give you the intuition behind what we've been doing with the IO monad earlier in the course.